Alright, this video is to help walk you through the lab analysis for your density lab. So we have two data tables. One is with 6 different size pieces where we have the mass and the corresponding volume. And for the other data table we used piece 2 and we repeatedly measured the mass and the corresponding volume to calculate the average volume. So you need to graph by hand the mass versus volume. Normally you'd put the mass on the x and the volume on the y-axis since mass is the independent variable. However, for purposes of this lab, we are going to put mass on the y-axis. So I've already graphed that, and my data looks like this on the graph. So there's my data. And we need to draw in a best fit line. A best fit line does not connect the dots. It is an average of all of the points, but it is going to be a straight line. And my best advice for a best fit line is to draw a straight line where there are the same number of points above the line as below the line. So here's my best fit line, and as you can see I have a couple of points above the line and a couple of points below the line, and this one almost actually hits the line. The best fit line averages all of the points together, so it's a nice way of reducing variation. So now we need to calculate the slope of the line, which is just rise over run. I'm sure you've calculated slope before in your previous math classes. It might not have been recently, so we'll go over how to do that. You need to pick 2 points on the line. Don't pick dots from your data set. Pick points on the line to calculate the slope. And it's easiest to pick points that cross the grid lines exactly, like this. So I've picked this point and this point, and as you can see I don't need to estimate what these values are very much. I just need to read the graph. So this point is 50. And the other corresponding y point Alright, so this point is 50 and the corresponding y point is 40. So we would mark that spot as 50/40. And then our other point on the graph, the x value is 12.5. And the corresponding y spot, y is 10. Alright, so we need to calculate the slope. We have our 2 points that we're going to use, and if we go to our next sheet of paper, let's clear that out, we can calculate our slope. Now slope, as I've already said, is rise divided by run, and slope is also given the variable letter m. So our y points, our 2 points were 50, 40, and then 12.5, 10. So our 2 y points that we need to subtract are 40 minus 10. And we will do that in parentheses because that gets done first. And we need to subtract that by the difference in the x points, which is 50 subtracted by 12.5. Alright, so if we do that, we end up with 30 divided by 37.5. which we can use our calculator here, is 0.8 grams over milliliters. So this is our experimental density, and I wanted to spend a quick second and talk about why that actually is the density. So when you calculate slope, it's rise over run, and it's the y values divided by the x values. Density, to calculate it, is mass divided by volume. We put mass on our y-axis and we put volume on our x-axis. So when we took the difference in these two values and then divided the mass by the volume, that ends up getting the experimental density. So that is the density. Give that a big asterisk, if you will. We need to calculate the y-intercept. And if we look back on the graph, our y-intercept actually is 0 for this particular example. Your y-intercept might not be 0, it could be 10, it could be 20. It's whatever value you would read where your best fit line crosses this y-axis. So that's how you figure out the y-intercept. So ours is 0. The slope of the line is y equals mx plus b. So y equals the slope, which is 0.8. times x plus b. In this case, b is 0. So the slope of the equation of the line is just y equals 0.8x. Why is this useful? Because I can give you any volume and you can substitute that in for this x value, because we put the volume on the x-axis, multiply it by 0.8 and it will give you the corresponding volume, or vice versa. The corresponding mass. Or the opposite is that I could give you the mass and you could calculate what the volume is. So that's why the equation of the line is useful. So we have two more things to do actually. We are going to calculate how accurate our data was by calculating the percent error. The percent error is just the difference between the experimental density and the known density divided by the known density. And then we'll multiply that by 100. So our experimental density we just calculated on the previous page, it was 0.8. So we need to take the difference. Our known density is the actual value. It's what you'd look up on Google, for example. And this orange substance had a known density of 1. So 1 minus 0.8 divided by the known density, so 1, and times 100 to get us a percent. So 1 minus 0.8 is 0.2, divided by 1 is still just 0.2, and then times 100. So our percent error is 20%. I'm not going to use a word like good or bad to describe the percent error. The percent error is 20%. If you have a percent error of less than 10%, you can say it's pretty accurate. It really depends on what you are doing and how you are measuring it, on calling it accurate or inaccurate. But we can actually quantify what the accuracy is by calculating the percent error. Lastly, we are going to calculate the variation for our repeated trial. So here's our data set again. We look at variation to see how precise or how repeatable the data is. And to calculate the variation, we need to do two things. We need to calculate the range in the volumes for our repeated trial. So we want to find the highest value and the lowest value. So 24 minus 23. Pretty easy to do, but I'll write it down. So our range for our repeated trial of piece 2 was just 1 milliliter. And then we have to look at the corresponding volume range and find the highest value and the lowest value and see how much that changed. So 65.6 minus 14.1 equals 51.5. So you can tell just by looking at it that the variation, this is natural variation just when taking measurements in a lab. That's what this is measuring, just random variation in a lab. But this variation was 1 milliliter versus looking at our actual data set, the volume had a variation of 51.5 milliliters. So this value is much, much, much smaller than this value. And you can say that the data is pretty precise because the variation is small for the repeated trials. If you want, it's always nice to quantify what it is, and you just would calculate what percentage 1 is of 51.5 by doing 1 divided by 51.5. And when you do that out, you would get about 2%. So you could say that the variation in the measurements accounts for 2% of the total variation of the lab. And that is how you would do the analysis bits for your density lab. Thank you.